angles opening to the same arc. Here you can see on this circle, this is an arc. An arc is a portion of the circumference of the circle. Now you can see also in this circle there are two different angles that open to the same arc. One of those two angles is called a central angle, right here. A central angle is an angle whose vertex is at the center of the circle. The second angle that opens to this arc is this blue one here. That is called an inscribed angle. It is an angle with all three of its corners on the circle. So the vertex is now on the circle instead of at the center. We're going to see some important relationships between inscribed angles and also between inscribed angles and central angles in this video. Let's recap the theorems we've seen so far. We've seen Thales' theorem, which tells us when you have an angle opening to a diameter or an angle within a semicircle, it is 90 degrees. We've seen a chord theorem, when you have a chord in a circle and then you have a segment from the center perpendicular to that chord, then the chord is bisected, meaning that we have AM equals MB. Theorem 3 was about a tangent on a circle and how it meets the radius to the circle, and they always meet at a 90-degree angle. They are perpendicular. And theorem 4 was about two tangents on a circle that meet at the same external point. Those segments created between the external point and the point of tangency, those two segments are equal in length. Okay, today we'll see two new theorems, but first, let's open our study guide. So please open the document you've been creating with your theorems and circle vocabulary. Now that you've opened that, you have added many definitions at the beginning. Right now, to begin this video lesson, you're going to add some more definitions, some other important words you need to know when working with circles. So here's the definitions you've added so far, and these as well. And now let's add some new definitions. Definitions to our study guide. First, add these. In this one, please note the difference between a minor arc and a major arc. A major arc is something beyond 180 degrees. Next, add this one about major and minor segments. And finally, add these definitions here. And these are this one at the end is the one that's going to be particularly important for what we're doing today. Here we can see this minor arc, BC, subtends the angle BAC. Okay, theorem 5. So as we've been doing, first you're going to hypothesize, make a conjecture. That means looking at this diagram, can you note some kind of relationship that might exist between the two angles that are marked in red here? Okay, let's investigate that in GeoGebra. And here I am in GeoGebra. Okay, remember when you go in GeoGebra, and you're going to follow these steps as well to create your own diagram. Always when you get in, first select geometry. Okay, now we're going to do some constructions. I'm going to hit more here. And the relationship we're trying to show first is this one. We want to create a central angle and an inscribed angle. Okay, so let's begin with a circle. There's my circle. To create a central angle, I'll need another point on this circle, so I'll add that point here. Okay, now I want to create the angle, so I'm going to use the segment tool to create the segments that make the legs of the angle. There's one segment, here's another segment. So now I have my central angle. Next, I want to create an inscribed angle. And the inscribed angle in our relationship, the inscribed angle should have the same 2 points here. So it's an angle that opens to the same arc, AB. So if I want an angle that opens to the same arc, I'm going to create another point back here, and now I'm going to make an angle that opens to the same arc BC. So there's that segment and that segment. So now I have that relationship created. I have my central angle, my inscribed angle, they both open to the same arc. Now we're trying to find a relationship between these two angles. So let's measure the angles. using the angle measuring tool. I'm going to measure the inscribed angle first. There's my angle measure. I'm going to move it a little bit so I can see it better. Okay, great. Now I'm going to measure the central angle as well. Measure the angle and the central one. Okay, there it is. And I'll move that measure as well. Now, on yours, you've created this now. Grab your move tool and move either one of these points, B or C, and make the angles bigger and smaller, and then try to note the relationship between the two angles. Do you see a relationship between the two angles? I'm doing it here as well. Okay, do it on yours and carefully observe the relationship between the two angles. It might be easier to see when the angles are whole numbers and not decimal numbers, so try it now. Okay, what you should have found, for example, here, I made the angles two whole numbers. I see the inscribed angle is 50, and at the same time, the central angle is 100. So it looks to me like the inscribed angle is half of the central angle. Or, said in reverse, the central angle is double the inscribed angle. Let's confirm that with two other measures. So here's 50 and 100. Let me go to make this one 40, let's say. I'll make this inscribed one 40. There we go. I made the inscribed one 40. This one's 80. Looks like the relationship holds, and that is a key relationship for today. Let's go back to the presentation. Please add theorem 5 to your study guide now. So where you have theorem 5, add this definition and add your diagram. Here's a diagram that shows what we just saw. Angle AOB, which is this central angle, is twice the inscribed angle ACB. And you will add your image from GeoGebra, so whatever you were able to create, please paste that into your study guide now. Fantastic. Let's do the other theorem. Oh, actually, before the other theorem, let's take a look. So here's the relationship you just found. I just need to point out some things to you. All right, so again, we found that this angle, the central angle, is double the inscribed one. That's the relationship we just saw. Now, here are three other examples of that. I want you to look at each image carefully and make sure you still see the same relationship, because it's easy to see when the angles are kind of like this, but what if they're like this? It's still the same thing. We have a central angle here, and here's an inscribed angle opening to the same arc. Even though it's a little more twisted than this one, right? We can still see this one is double this one. Now here, this one's probably the hardest one to see, but it's the same thing again. Here we have the central angle, which is this big one, opening to this big arc. So now it's opening to a major arc. Here, it was opening to a minor arc. Here, it's opening to this major arc. So this angle, 2 alpha, opens to this major arc. This inscribed angle also opens to the same major arc. So then this angle, the central angle, is double this inscribed one. Okay, this one's kind of harder to see. Finally, here's another version of it. Here we have the central angle, which is double the inscribed angle. And even though they kind of share this same side here, you can clearly see that this inscribed one and this central one both open to the same arc. So it's all about spotting the arc and the angles that open to them. Now, something you may have noticed is that this theorem is kind of like or basically a theorem we've seen before, this one here. This is Thales' theorem, the one where an angle opens to the diameter, or an angle is inscribed within a semicircle. That angle we knew was 90. Well, that theorem is basically a version of the one we've just seen, because here, if you look at this central angle, this angle, which is basically a straight line, but it's still an angle, it opens to this arc, which is a semicircle. That angle is 180. Now this inscribed angle opens to this same arc, and it is 90. So notice this central angle is double this one. So that's a nice connection between two theorems now. Okay, let's move on to theorem 6. In this theorem, we have two inscribed angles opening to the same arc. So it's no longer inscribed in central angle, it is now two inscribed angles opening to the same arc. What conjecture can you make here about these two angles? What do you think? All right, let's investigate this one in GeoGebra as well. So please join me in a new GeoGebra window. I'm going to go to geometry once again. And let's create that situation. We need a circle with 2 inscribed angles. There's my circle. I need more points. I'm going to put a point here. I'm actually going to move this point a little bit. Move this point a little bit. Okay, so here is my arc, BC, and I need to create 2 inscribed angles to that one. So I need more points. Here's 1 point, and I'll make an angle here. Okay, so C to D, and D to B. Okay, I made 1 inscribed angle opening to this arc. Now I need a second inscribed angle opening to the same arc. So I need another point. I'll put it here, and I'll complete that angle as well. There's my angle. Okay, 2 angles opening to the same arc. However, in this diagram, it's kind of hard to see the angles, so we're going to actually use the move tool, and I'm going to change the color so the 2 angles are distinct. So I'm going to click on that segment, and here it has the color. I'm going to hit red for this one. I'm going to make the other leg of this angle also red. Okay, so that angle's in red, it's easier to see. Now the other angle, I'm going to make in a different color. So maybe I'll make it blue. Okay, there, and this segment also, and it's blue. Great. So I have the red angle, 1 inscribed angle, blue angle, another inscribed angle, both opening to the same arc. Now let's see what the relationship between the 2 angles is. So I'm going to measure those 2 angles. I've measured the first angle. I'm going to move that so I can see it there. And I'm going to measure the second one now. Measure, angle. There it is. Move that label a little bit. Well, it's clear already. Look at the 2 angles, exactly the same. We should double check that by moving these vertices and to see if the angles remain the same. Okay, that one's 43 still. That one's the same. So both angles, inscribed angles, when they open to the same arc, remain the same. So now let me change the size of the arc. I'm going to grab one of the 2 points here. Changing the size of the arc. Both angles still open to that arc. And notice the angles remain the same measure no matter how big the arc becomes, right? So 2 inscribed angles opening to the same arc have the same measure. Okay, great. Let's add that to our theorems, and we're just about done here. Just investigating the second theorem in GeoGebra. Now let's add it to our study guide. So add it as, oh, that's not right. That should say theorem 6. Let me change that for you. Okay, so theorem 6, add that to your study guide. Angles subtended by the same arc, and they are equal. So you can see here ADB is equal to ACB. Also into your study guide, after adding the angle description, please add the image you have created in GeoGebra. Fantastic. Let's do 2 practice problems to make sure you know how to use these 2 theorems you've discovered today. So grab your notebook, let's take some notes. Here's the first example. Please draw this diagram. Our goal is to find the measure of angle x. In this one, first of all, we can note that if this is x, this is 2x. That is the theorem we just saw about a central angle and an inscribed angle subtended by the same arc. Okay, the central angle is always double this one. So we need to find x. We know this is double that. We know this is 250. Now, if this angle here is 250, do we know what this angle here is? Well, yes, we do. We know that angle AOB, this angle here, is 360 minus 250, because all the way around here would be 360 degrees. We subtract 250 to get this angle here. So that angle must be 110. Okay, angle AOB is 110. Now that we know this is 110, we know this one must be half of that. So 2x equals 110. Therefore, x equals 55. Okay, so pretty, not too complicated application of that theorem. Make sure you have all these steps written down. Make sure you have your reasons in parentheses along these different steps here. Okay, one more example. Here you can see it is probably about 2 inscribed angles. Okay, so it's a little harder to see, like I said, in this diagram. So sometimes it helps for students to mark different segments, but I'm looking at this and I'm saying I'm only given one angle here, this angle here. Okay, so angle ACD. And I look at ACD and it opens to arc AD. Okay, this angle here opens to this arc. Is there another angle that opens to there? Yeah, there's the angle ABD. It also opens to this same arc. So that means ABD must also, see there's the arc that they both open to, this angle and this angle. Now that means that this angle here must be 36 because they both open to the same arc. That's the theorem we just saw. So ABD is equal to ACD, angles on the same arc. That's what I just marked here. Okay, make sure again that you really think about both of those open to the same arc. For a lot of students, it's hard to visually see that with all these lines here. Okay, now that we've established that, does that help us get this angle? Well, there's a relationship between parallel lines. And notice in this diagram, we also have this line is parallel to this line. That's what this little arrow means, that these are parallel. And when two lines are parallel and they are cut by a transversal, this is something you've definitely learned in geometry. There's relationships between the angles. For example, this angle and this angle here, they are called alternate interior angles. And alternate interior angles are always the same. See, equal alternate angles. BDC, BDC, this one here is equal to ABD, this one. So these two are actually equal. That tells us that x must be 36. Done. Okay, so some properties there to think about. Ponder it a little bit, and we'll see you in class to try some more problems together. Great job.